Okay, so welcome everyone. Today we will have Kevin Young from Stanford. He will be talking about KPZ equation from ASEP with slow bond. So Kevin, you can take it away.
All right, thank you, Cheyenne, for the invitation to speak and the introduction. It's certainly a very nice pleasure and opportunity. So, as Cheyenne just said, the plan for the talk is to talk about this ASEP with slow bond model in the context of what's known as the weak-KPZ universality conjecture. So the main player in this weak-KPZ universality conjecture is this KPZ equation, which is stochastic PDE. And mathematically, it's stochastic PDE that starts with this linear equation. That's everything that's not in pink. And then you add this quadratic function of the slope into the equation. So mathematically, it's the stochastic PDE, and maybe more the physics or probabilistic direction. The solution is supposed to provide a model for the height function or some interface or growth model. And it's not just a model for height function, but it's supposed to be a canonical or universal model for a height function. And it was derived for this purpose, actually, by Carter, Parisi, and Zhang in '86. And what do I mean by universality exactly? Well, it's supposed to be universal as a height function model for growth or interface models, which exhibit three growth mechanisms, each of which correspond to a term in the right-hand side of the equation. And the thing that makes KPZ is the quadratic function of the slope. So this nonlinear function in the equation. So before, and I'm happy to send these slides to anybody who wants them, by the way. So before I talk about what KPZ universality is, or weak KPZ universality, I want to give at least one model of an interface or growth model that's supposed to be described by this KPZ thing. And the model is a dynamic easing model. So we have two faces, a plus and a minus phase. And the interface that we're going to be interested in is this sort of boundary between these two phases. All right, so we start with this initial configuration. And how does this thing evolve? What's the process? In short, and I'll explain this, what we do is we impose a zero temperature Glauber dynamic with weakly positive magnetic field for the spin system. So Glauber dynamic just means the spin will update according to a speed determined by its neighbors. The zero temperature condition forces that only the spins next to the boundary can update. And then the weakly positive magnetic field will favor the plus phase. And this is the thing that will give the slope dependent growth mechanism in the interface. So if you want, really, it's not zero temperature, it's very small temperature. And you can sort of map this heuristically onto ASEP, which I'll discuss shortly, and maybe see KPZ from ASEP. But this is just one example of an interface or growth model that's supposed to be described by KPZ. Other ones, in some sense, are the Eden model, ballistic deposition, at least conjecturally. And then more of the focus of this talk, height functions associated interacting particle systems. Oh, I also meant to say, if you have any questions, you should feel free to interrupt me, however, and I'll try to keep my eye on the chat as best as possible. Okay, so why is this weak KPZ universality a little interesting? Sort of what is this problem? Where does it actually come from, this universality? Before I say anything, I want to highlight that the sort of thing that makes it interesting is the singular nonlinearity equation that I'll explain in a bit. So to see where the universality comes from, one thing that's effectively done in this Carter, Parisi, Zhang physics paper, and I emphasize physics because it's non-rigorous, is to consider the solution H epsilon to a generic stochastic PDE in the middle of the slide. So if we took f to be a quadratic function, then this would recover KPZ at the top of the slide. And the problem of weak KPZ universality can be thought of as in the small epsilon limit, I want this stochastic PD in the middle of the slide to turn into KPZ. One way to do that is to Taylor expand the function at around 0 with respect to the slope that we're inputting into the function. And now here's the first observation. The 0th order term and the 1st order term, when we plug that back into the equation, we can actually get rid of these terms through elementary transformation or change of coordinates. So for example, if we plug the 0th order term back into the equation, we can get rid of this thing just by replacing H epsilon by some global drift in space. In terms of the physics, this doesn't actually change the problem. This is actually something that we might expect. And I'll come back to this slide. But for example, in this dynamic easing model, there's a weakly positive magnetic field, which means that the plus phase is favored over the minus phase. And that means that the plus phase is going to invade the minus phase. So this whole interface between the two phases is traveling with a global shift. And all we're doing when we remove that 0th order term is following that global shift and then looking at the fluctuations about that global profile. And the 1st order term right here, when we plug that into the equation, we can get rid of it by following some constant speed characteristic of the fluctuation statistics. The kicker being that the first 2 terms can be removed through elementary transformations. And when we plug it back to plug it back into this equation, and then we're left with this quadratic term plus terms that have positive powers of epsilon. So when we take epsilon to go to 0, we expect this stuff to go away and we get KPZ. And it's not just that, we actually expect to get KPZ in the small epsilon limit with an explicit coefficient in front of the quadratic thing that's predicted by this sort of second derivative evaluated at 0. Now, this is where things get a little interesting. This ends up being the wrong answer. So more precisely, what do I mean? It is true that H epsilon does turn into KPZ in the small epsilon limit, which is sort of the point of these papers that I listed here. However, the coefficient in front of the quadratic nonlinearity appearing in the limit KPZ equation is not this term predicted by Taylor expansion. It's actually given by averaging against some Gaussian measure or some invariant measure type thing. So one way to interpret this sort of wrong answer is, again, this singular nonlinearity feature of the equation. So if we think of KPZ perturbatively around the linear part, so if we forget the quadratic term in the equation, the solution to that linear thing is supposed to look Brownian as a function of the spatial variable. So perturbatively, we expect the solution to KPZ to also look Brownian. And in that case, it doesn't really make sense to talk about this thing. This thing is sort of infinite. So in particular, if we look at this Taylor expansion, the higher order terms past the quadratic thing do have higher powers of epsilon, but they also have higher powers of this gradient, the slope, which is singular. So the epsilon is competing with a singular thing. And particularly the higher order terms do contribute to the limiting quadratic in the KPZ. So this list of papers at the bottom of the slide effectively do this type of calculation correctly and rigorously. So every paper listed here that has Heyer as an author approaches the problem with regularity structures.
So the coefficient is different, you were saying?
Yes, the coefficient is actually given by where the expectation is with respect to a Gaussian measure. So this x is distributed as normal, 0 some variance.
I see. Okay.
Yeah, so what happens is that this sort of singular effect, things are oscillating very quickly, but by oscillation, what really happens is that things start to average out with respect to an invariant measure for the equation, which is this Gaussian. Another way of thinking about this is that integration by parts tells us this thing is the expectation with respect to f itself, but times the second Hermite polynomial. So really the expansion should be done in terms of Hermite polynomials. So the higher papers use regularity structures. The Gubinelli-Frykowski paper uses energy solution theory. The upshot there is that it can treat a larger class of nonlinearities for these generic SPDE models, but the constraint is that the initial condition has to be a Brownian motion because of invariant measure considerations. And this last paper of myself removes the assumption on that initial condition through a maximum principal type argument. Okay, so this is, in a nutshell, the weak-KPZ universality picture for SPDE height functions. I do want to stress that maybe as indicated by the title of this talk, the focus is going to be more on height functions associated with discrete models for interacting particle systems. But to sort of tie up this story about this not singular stuff in KPZ, there are many ways that one can interpret the KPZ equation. So regularity structures, energy solutions, or para-controlled distributions, all of this very modern advanced technology. But the one I'm going to take is the Cole-Hopf transform, which is the one that's maybe usually taken, not usually, but often taken for interacting particle systems in the context of weak-KPZ universality. And maybe in the spirit of this seminar, this is also where we start to see the integrable features of the KPZ equation. So I have this KPZ thing, and then the Cole-Hopf transform proposes a solution for this thing. So this was really developed in '96 by Bertini and Giacomini. Instead of solving the equation, the KPZ thing directly, what we do is we simply define it through this logarithmic transform where the Z process solves the stochastic heat equation with a multiplicative noise, which is this thing. So the Ito formula with respect to the space-time white noise will actually take one between the two equations. Formally, it's not a rigorous calculation because of sort of regularity considerations in the noise. But formally, one goes between these two equations through this logarithmic transform, which is one motivation. The upshot to this definition is that the stochastic heat equation right here that I underlined, you can solve this thing with the Ito calculus and sort of none of this now modern technology. And by solve it, what I mean is interpret it as an integral equation instead of a differential equation. And this integral equation admits a solution courtesy of the Ito calculus. And the Ito calculus, at least in 1+1 dimensions, spits out something that's a bona fide function. And Mueller tells us that this function is positive as long as you start with initial data that's non-negative and non-zero. And what that means is that we can actually define this logarithm. So this is an honest thing to do. We can actually do this rigorously. The sort of upshot, maybe to spoil the story, maybe some of you know the story, it agrees with every solution theory that I mentioned before as well. Okay, so there are no stochastic analytic difficulties with this equation, the stochastic heat equation right here. This is sort of the benefit. Okay, so as I said on the previous slide, I want to sort of focus on interacting particle systems in the context of this KPZ thing. And the prototype particle system that's usually talked about for these models is the ASEP, which is short for the asymmetric simple exclusion process. Before I say what it is, I want to emphasize that ASEP is one of these integrable models or solvable models, at least partially. And I'll explain what I mean by that shortly. Yeah.
Sorry, Ken, one question. So you said that the stochastic heat equation can be solved using Ito calculus.
Yeah.
But is it possible to recover these exact solutions, which maybe you will mention or not, which one can obtain as a limit of the ASEP, for example?
Oh, so is the question like these duality formulas with the area point process and stuff like this?
So there will be some this solution.
Yeah.
Either you say it can be calculated using Ito calculus or using these solvable models. And has anybody managed to match these two techniques?
Oh, well, I can tell you the picture I have in my head, and then you can tell me if this answers your question. So these solvable models and these sort of exact formulas that one gets for KPZ come from finding formulas for discrete systems like interacting particle system, vertex model, stuff like this. And then sort of taking a limit in some sense, and then turning these formulas into formulas for KPZ. Somehow you need to justify that these discrete systems actually converge to KPZ. And this is, for example, what's done for ASEP. So, and I'll talk about this on the next slide, but roughly speaking, there's a height function associated to ASEP, and it was shown that this thing converges to KPZ. And for example, this is where you get a lot of the integrable structure of KPZ. But to actually show this convergence, one has to make sense of solving KPZ in the first place. And this is how it's made. This is how it's solved in the context of exact formulas. Does that answer the question?
I mean, if one can match exactly the formulas as one can get, for example, explicitly solving the stochastic heat equation with the determinantal formulas.
I think it's sort of the formulas for KPZ that are sort of determinantal hold if sort of, it seemed, I think it's tautological at some point. If we define this to be the solution of KPZ, then we get the determinantal formulas.
Okay, I'll think about this.
Okay, yeah, and if someone else has something to say, you should say something.
I think what Thea was saying, like in stochastic heat equation, there are like previously known like this moment formulas, like the integer moment formulas. So I guess like I don't know if those are like rigorously proved, but at least like Carter has some like guess for this moment formulas for the stochastic heat equation, or which you can think of it as like exponential of the KPZ. Now the question is whether like this determinant formula of the KPZ that you get after taking the limit of this discrete formulas, whether that would give you the same moment formula, and it indeed would be giving the same formula. That has been checked. Yes.
So this Ito calculus is the replica trick.
Yes, yes. So you can use the replica trick to come up with the formula, and you can match that with the formula that you get from the discrete model.
Oh, I see what you're saying. Thanks for me. Does that answer the question, Matteo?
Absolutely.
Thank you. So ASEP is a system of particles on the one-dimensional lattice, which first, every point in the lattice has at most one particle, and then these particles perform independent asymmetric simple random walks, subject to an exclusion constraint that prohibits particles from jumping onto other particles. So here's a little graphic of what ASEP might look like in a couple steps. And the speed of the asymmetry is of order n to the -1/2, where n is some scaling parameter going to infinity that's going to turn ASEP into KPZ. So associated to ASEP is a height function, and this height function is fairly easy to describe. Given a particle configuration on the lattice, we can prescribe a simple random walk path that goes up by 1 if there's a particle at that point, and otherwise it goes down by 1. So because ASEP is a process on particle configurations, there's a canonically associated process on the height function. And this is the height function process that's supposed to give us KPZ. So we'll do this calculation later in the talk, but the magical thing is that the stochastic equation for the height function growth is a discrete version of KPZ. So these differential operators here are discrete differential operators. And this is sort of a miracle, because even if we know that H turns into KPZ under some rescaling or whatever, some renormalization, the stochastic equation for the height function doesn't have any error terms. It's sort of an on the nose exact discrete KPZ. And it might be believable that you can just follow your nose and show that H turns into KPZ under some normalization. This is in fact what's done in Bertini and Giacomini's 96 paper that I talked about earlier, except they don't actually look at the height function directly using this equation. What they do is they actually look at the stochastic equation for the exponential of the height function. The reason being that if you want to work with this equation that I drew an arrow to, this microscopic KPZ thing, you want to show directly that this thing turns into KPZ, you'd have to make sense of the singular term in the equation. And by the particle system structure of the noise, this ends up being very difficult. And in particular, I at least don't know of anywhere where it's written down how to do something like this. So it's done via the Cole-Hopf transform. And just to get a little taste, the fact that Bertini and Giacomini can look at the stochastic equation for this Cole-Hopf transform and then follow their nose, roughly speaking, is really the integrability of ASEP that's being used here. And that integrability is being hinted again by the fact that the stochastic equation for the height function doesn't really have any error terms. So that's the story for ASEP. For this talk, I'm going to be talking about ASEP with the slow bond. And what I want to say first is that ASEP with the slow bond is not integrable. Sort of as soon as you introduce the slow bond, you lose the integrability. And I also want to say that this model is not just a perturbation of ASEP. And we'll see that later as well. So ASEP with the slow bond is the same thing as ASEP, except for the bond between 0 and 1, the symmetric component of the particle of random walk now has a speed of n to the minus beta star, where beta star is some fixed positive exponent, independent of the scaling parameter. So ASEP with the slow bond is, at least in this talk, is a perturbation of the symmetric component, whereas we haven't touched the speed of the totally asymmetric component in the ASEP model. So here's a little graphic. The slow bond is in yellow here. So it's still a process on particle configuration so that you can tell the same story with the height function. And maybe not surprisingly, the stochastic equation for the height function is basically the one we had before, discrete KPZ, but now you have some slow bond errors. So there are error terms in the height function for this thing that aren't sort of naively small because this model is not just a perturbation of ASEP. And this is already a sign that this model is not integrable. At the level of the height function, you can think of this corner growth model as, this height function as a corner growth model with local defects at the slow bond. So this model isn't just sort of one that I threw out there. There's actually a sort of rich history of slow bond exclusion models. So in '92, Janowski and Lebowitz effectively asked the question. So they asked in terms of currents, but we can ask it in terms of the height function if you want. How does the height function change at the slow bond? So they really asked the question for speed 1 TASEP, which isn't the model I'm talking about, and where they changed the slow bond, the speed of the slow bond to be any speed strictly less than 1. And their question was, does this have any effect on sort of the height function at large scales? So I was doing some reading of the literature before this talk, and I learned that this question was, in some sense, if you want to call it controversial, because it wasn't really clear what the answer should be. So the math and the physics communities had very different answers, but the question was largely settled by Basu, Sierravicius, and Sly 7 years ago, I guess, at this point. And they said that there is a change when you introduce the slow bond. So to be precise, they work with step initial condition for TASEP. And their techniques for resolving this question was borrowing something of the integrability of TASEP and then giving some other ideas, which they called geometric. And so that's one part of the story for the slow bond stuff. And then several years ago, Franco, Goncalves, and Simon asked for the actual ASEP with slow bond model from the previous slide how does the height function change with the slow bond? The answer that Franco, Goncalves, and Simon gave is that at least when we give the asymmetry n to the -1/2 scaling, there's no change in the height function. So we still expect this thing to go to KPZ. So they work with an invariant measure initial condition so that the particle system starts at an invariant measure. And the reason for this is because they heavily depend on this energy solution thing that the Kubinelli-Perkovsky paper also depended on before, and their techniques are entirely probabilistic. So ASEP with a slow bond is not an integrable model, which means that these authors have to do something different than what Bertini and Giacomini did. And what they end up doing is sort of totally orthogonal to the integrability that was present for ASEP. So the motivating question for this talk, at least for me, is what about general initial measures? And being able to prove something for general initial measures would be a genuine step towards weak-KPZ universality, because it would indicate that the height function for ASEP with a slow bond would turn into KPZ as a consequence of the actual particle system process and not just the initial condition. Okay. So Franco, Goncalves, and Simon actually do something a lot more than what I just said. They actually take they take a one parameter family of rescalings of the asymmetry, and they end up getting some type of phase diagram which shows the effect of a slow bond, which I've written here. And I don't really want to talk about the details of this. What I want to say is that we're going to be focused with this KPZ part where the strength of the asymmetry is n to the -1/2. But just to give a little taste of what the slow bond can do. So in the case where beta star is bigger than 1, we don't see any KPZ stuff because the strength of the asymmetry has to be at least the strength of beta star to make the model well defined. So what we get instead of the Laplacian in the limit SPDE is a Laplacian with a Neumann boundary condition. And just to illustrate where the Neumann boundary condition comes from, if I have a random walk, that's sort of the speed of crossing 0, 1 is much smaller than 1/n, then the probability that the random walk is going to actually cross this thing at macroscopic scales is going to 0. So we get a random walk that's sort of staying strictly to the left and staying strictly to the right. And this is, in the large n limiter, reflecting Brownian motion, which is the reason why we see a Neumann Laplacian in the limit SPD. So this is just to be totally honest about what Franco, Goncalves, and Simon actually do entirely. But again, we're going to be focused on this KPZ part.
Oh, can you remind me what was the gamma parameter?
Yeah, sorry, gamma, this is the, yeah, exactly. Sorry about that. Gamma is the strength of the asymmetry. So it's the exponent.
Oh, I see.
So if we take gamma to be 1/2, then we get the KPZ. So what I want to sort of just point out in this slide is that you can consider a much larger generalization of exponents than I did in this talk so far. And you do see some interesting behavior, even if you're outside the KPZ world. So I'm going to recall that the point of this talk was to talk about height function for ASEP with slow bond, turning into KPZ under some renormalization and rescaling. So the first thing I have to tell you is what the renormalization is. And it starts with parabolic scaling in space-time. Sorry. And this is just because the limit equation is the Laplacian. That's invariant under this scaling. And then remember that the height function is supposed to be Brownian at large scales because it's supposed to look like KPZ at large scales. So Brownian motion of length n, we have to scale it by n to the -1/2 to get an order 1 thing. And then because of the asymmetry, similar to this dynamic easing model, there's going to be a global shift in the height function. So we have to counter that global shift, which is the reason for this term. And to be a little more explicit, the speed of the global drift is given by the flux, sort of an averaged flux of the particle system, which means in particular, it only depends on the asymmetric part up to leading order. So the speed of this drift is blind to the effect of the slow bond, at least up to leading order. So the theorem, the main result of this talk is that under this renormalization, the height function for ASEP of the slow bond turns into KPZ, as long as the initial condition is reasonable, and beta star, this sort of strength of the slow bond, is sufficiently small, but it's still fixed and strictly positive independent of it. And I'll talk about the utility of this assumption later. But first, I want to say that reasonable here is an analytic condition and doesn't have anything to do with being close to an invariant measure, sort of in law, for example. The reasonable here just means, right, so we want to solve KPZ and we want this thing to turn into KPZ. The reasonable thing, the reasonable property that I stated here just means whatever we start with should be reasonable enough that we can actually solve KPZ with that initial condition. But otherwise, there's no other constraint on the initial condition. So small for beta star could be made quantitative in the sense that if you follow the proof of this thing very carefully, you can get an explicit beta star that works. And it seems like beta star being 10 to the minus 10 million would probably work, though you could probably do better than that with our methods. The interesting thing here is that beta star could be made bigger if we're closer to the invariant measure initially. So I should say that the Franco, Goncalves, and Simon group that worked at the invariant measure considered all beta star between 0 and 1/2, which are the values for which the model actually makes sense as a Markov process. But we can only work with beta star small, but we can sort of make it bigger as we get closer to the world that Franco, Goncalves, and Simon are working. What I want to say next is similar to Basu, Siderovicius, and Sly's paper. So remember, they borrowed something from the integrability of ASEP, and then they gave an additional ingredient. We're going to do something similar here. We're going to borrow something from the integrability of ASEP, and then we're going to give additional analytic and probabilistic ingredients. Something I do want to preface and sort of hint at for now is that this is going to amount to approximating the integrability of ASEP. And something that I learned in the course of working on this problem, is that approximating integrability is sort of not a canonical thing. There are many ways to approximate the integrability of ASEP, some of which are better than others in certain contexts. So that's going to be maybe the main theme in terms of the integrability aspect of this talk. But then in terms of additional questions, there are a lot more than the ones I wrote down here. Can one get a better value of beta star? So can one get bigger values of beta star and prove this theorem? Still, it's not exactly clear how far the methods that are actually used to prove the theorem can go. In particular, I don't think you can get close to the maximal value of 1/2 with the methods that I'm going to be talking about today. So that would certainly be an interesting question. Another interesting question would be how much of this phase diagram from the previous slide can I actually, can not me necessarily, but can one actually recover Franco, Goncalves, and Simon's results away from the invariant measure? So for the rest of this talk, I want to talk about, I want to focus on the integrability aspect of this theorem, but then I will say something about the non-integrable aspects as well, because those are very important. So this also,
sorry.
Yeah.
Before you, can I ask you, is it is the invariant measure of the ASEP with slow bond explicit?
Yes, sorry. So that's a great point. It's the same as ASEP itself. So the slow bond doesn't change the invariant measure. So it's going to be this product Bernoulli measure as well. But I also do want to say that our methods also work if you perturb the slow bond in a fashion that totally breaks that invariant measure as well. So our methods aren't that dependent. But that's a great question. Okay, so to talk about what happens for ASEP with the slow bond, the first step is to figure out what happens for ASEP. So again, if you want to work with a microscopic equation for the height function, this is going to be very difficult because it's very difficult to make sense of the singular stuff in KPZ at the microscopic level. So what's done is to work instead with the microscopic equation for the exponential, or some microscopic version of the Cole-Hopf transform. So we exponentiate the microscopic height function. And the goal is to show that this thing converges to the stochastic heat equation. So by definition, this would give that the height function turns into KPZ. But so the exponential transform is a function of the height function. So for example, if everything were diffusion, we could write down an equation for the height function, then apply the Ito formula to get an equation for the microscopic Cole-Hopf transform. And that's effectively the case here, but it is sort of more detailed because things are jump processes here. But we start with the equation for the height function. And for this, I'll need a little notation. So eta tx is going to be a +1 if there's a spin at x in the time t configuration, otherwise it's a -1. And just because the height function goes up or down by 1, depending on if there's a particle at the site, these etas are also just gradients of the height function. And the end of the 1/2 scaling is just a consequence of the scaling that we give the renormalized height function. So the S terms, so an S with the right arrow means the speed of a jump from x to x + 1 at time t. And the S with the left arrow is the speed of a jump from x + 1 to x on the other leftward direction. And you can either reason this out just by using sort of a martingale decomposition for the height function as a function of the particle system if you want, or you can just sort of see what happens infinitesimally in the height function. But whenever there's a jump from x to x + 1, a peak is going to turn into a valley, which is all this means. And then whenever there's a jump from x + 1 to x, a valley is going to turn into a peak. So that's the drift in the martingale decomposition. In average, what happens in unit time. And this is the associated noise or martingale term. And this is sort of the magical thing with this ASEP model. The symmetric parts of the speeds, s to the right and s to the left, if we just look at those, they'll give us this Laplacian of the height function, plus some other order n quadratic terms that happen to cancel with the asymmetric part of the s speeds. So that what comes out of there is this sort of this nonlinearity of the height function, at least up to leading order. And this is where the stochastic equation for the height function comes from. And the magical thing, which is really the integrability of ASEP, is that this exact microscopic height function equation gives us an exact microscopic stochastic heat equation for the Z process. And at this point, Bertini and Giacomini more or less follow their nose and recover a stochastic heat equation from this. The upshot being that there are no stochastic analytic difficulties with this equation or its continuum version. So this is the story for ASEP. Now what happens for ASEP with the slow bond? Well, we can do the same thing, except now our speeds have changed. So S tilde is going to be the speed associated to ASEP with the slow bond. So the first observation is that away from the slow bond, the speeds haven't changed. They're the same as the ASEP speeds, which means that if we're away from x = 0 at the slow bond, we still get the discrete type KPZ equation for the height function on the previous slide. And moreover, we also even get the exact microscopic stochastic heat equation for the Z process. The issue is what happens at the slow bond. So at x = 0, and the starting point is the same. We still get this equation for the speed of jumping from 0 to 1 or 1 to 0 and then the effect of a valley turning into a peak, or a peak turning into a valley. But these S tildes are different from the S's, so they aren't going to sort of magically cancel and work out to give us the microscopic KPZ stuff. One thing we can do is we can just replace S tilde by S, in which case we get the microscopic KPZ stuff, but then we get an error term coming from replacing S tilde with S, because we can't just do that without changing the problem. And this error term is given by this yellow thing in the equation. It's of order n to the 3/2. So one way to see that is that the whole system is moving at a speed of n squared. And then the effect of a valley turning into a peak, or a peak turning into a value, induces the change of n to the -1/2 because of our scaling, and n squared times n to the -1/2 is n to the 3/2. Up to leading order, this thing looks like a to t0 minus a to t1. So it's what's known as a fluctuation. And by fluctuation, all I really mean is that the steps in the particle system will induce fluctuations into the value of little f. So for example, if we plot the value of little f in time, and we see a particle just jumping between 0 and 1, we're going to see the value of f go from plus to minus with every step. So this is one approximate integrability of ASEP with a slow bond. So I've rewritten at the top of this slide, and just remembering that all of these differential equations are really interpreted in terms of integrating against the heat kernel. So here, this fancy U is the heat kernel associated to the discrete Laplacian. This error term sort of becomes this integrated term of the heat kernel times the yellow thing. And now Franco, Goncalves, and Simon say that because up to leading order, this fluctuation term, this error term is a fluctuation term, because they're at the invariant measure, they're able to leverage techniques for stationary models for them to argue that this error term actually vanishes in the large n limit when we integrate in this fashion. So that's what happens at the invariant measure. So this approximate integrability works for them. Outside the invariant measure, well, none of these sort of techniques that they're able to use for stationary models apply in any capacity outside the invariant measure. So the tools that I'm talking about, in case anybody's familiar, is this Kittnes-Vardan inequality for stationary models. None of that applies for general initial measures, general particle systems. So one indication of why this thing might be difficult is that this heat kernel is of order 1/n. One way of seeing that is you can think of the heat kernel as just the Gaussian heat kernel, but it's evaluated at time n squared. So the 1/√t turns into a 1/n√t. So naively, we get a bound of n to the 1/2 for this thing, which is very divergent as n goes to infinity. And this is already a sign that whatever we do outside the invariant measure is going to be very difficult. One can still try to do this. For example, if one is sufficiently close to the invariant measure initially. But for general initial conditions, this is going to be very difficult. So the approach that we take to sort of go around this problem is a different approximation to the integrability of ASEP with a slow bond. So here's the martingale decomposition of peaks turning into valleys and valleys turning into peaks for ASEP with a slow bond. So for ASEP without the slow bond, the S's magically cancel to give us a Laplacian plus an order n quadratic thing that then cancels with the asymmetric part of the speeds to give us this quadratic thing in the height function. Here we can try to argue similarly. So these S tildes at x equals 0, remember, are just a slowed down version of the speed in ASEP by a factor of n to the minus beta star. So when we do try to use the same reasoning, the symmetric parts of the S tildes will give us the Laplacian of the height function, but with an additional factor of n to the minus beta star. And then the same order n quadratic stuff, but again, multiplied by n to the minus beta star. Now here's where the non-integrability kicks in, we haven't touched the asymmetric part of the speeds. So this won't cancel with the order n quadratic stuff in the asymmetric part of the speeds. So because we don't have this cancellation, when we write down the stochastic equation, after combining the effects of these things, we get an order n quadratic error term, which is good, by the way, because now the error term is of order n and not n to the 3/2. But the price that we have to pay is that the coefficient in front of the Laplacian isn't just a constant thing. Now it has a factor of n to the minus beta star at x equals 0. So if you want, the sort of takeaway from this slide is that sort of this alternative approximate integrability trades in the n to the 3/2 error term for a much more innocent one. But the price we pay is that we're working with not the Laplacian, but some perturbation. Once we have this equation, well, what do we do? So I've recalled that the coefficient is just 1, except if you're at x equals 0. So it should say that this Q functional it's not a fluctuation, so it sort of is a little not as good as the error term in the first approximate integrability, but at least its averaged effect with respect to invariant measure is 0. So in some large scale sense, we might expect this thing to contribute nothing at the large n limit. But there are 2 steps in the proof at this point. One is to show that at the level of heat kernels, we can forget about AX and we can just replace it by 1. And the second one is to show that the effect of this yellow error term vanishes when we integrate against the heat kernel in time. In terms of the first part, sort of showing that this thing is approximately the Laplacian, this is really just a PDE argument involving Nash inequalities and sort of no probability at all. The sort of interesting probabilistic pieces are in showing that this error term vanishes. And at this point, sort of the integrability aspect of the problem was gone. We sort of decided on an approximate integrability for ASEP with a slow bond. And now just comes the extra probabilistic and analytic ingredients. I should say that we don't, similar to Bertini and Giacomini, we don't actually work with the height function. We actually work with the microscopic Cole-Hopf transform, which ends up not really introducing that many difficulties in this problem, if any, really. And again, that's just because we don't want to have to make sense of the singular stuff at the level of the particle system. Okay, so I did have more slides about this, but I think maybe I'll just give a brief idea of what these probabilistic arguments are saying, and then I'm happy to discuss other things.
So where exactly do you need the beta star to be small?
Great question. So this 8x thing is not uniformly elliptic.
Okay.
Because of the n to the minus beta star at x equals 0. So you can think of it as like a random walk where the diffusivity is dying out at 0.
I see.
We want beta star to be sufficiently small so that it's not dying out too much. It's the x equals 0.
I see. Okay. Mm-hmm.
And there's also one that comes from sort of vanish. There's another sort of helpfulness of taking beta star small to be in showing this limit is equal to 0. And that corresponds to the fact that we need the particle system to sort of evolve at a sufficiently fast speed so that things can average out fast enough. Yeah, that's a great question. So in terms of the second step of showing that this thing goes to 0, first I've traded in the heat kernel for a 1/n just to sort of make things a little simpler to illustrate what the idea of this step actually is. So the first step, we have this quadratic thing. The first step is to replace the quadratic thing by replacing the spin at eta t1 by its average on some block of length n to the epsilon, some mesoscopic length scale. The justification of this step is this idea of local equilibrium. So at the invariant measure, this can be justified with the Kipnis-Varadon inequality. And in words, what that's saying is the following. If the particle eta T1 sort of communicates with the particle in this block from 1 to n to the epsilon, as sort of these spins exchange values, this thing is going to fluctuate. So similar to the eta T0 minus eta T1 functional that Bertini and Giacomini worked with, as the particle system evolves, as these spins in this mesoscopic block talk to each other, the value of the difference between, this thing and this thing is going to fluctuate. And at the invariant measure, the Kipnis-Varadon inequality helps us take advantage of this fluctuating behavior by taking mesoscopic time averages of this thing. So for example, you can think of it as like a law of large numbers. If you're averaging a fluctuating thing, you expect this thing to be 0. Outside the invariant measure, again, the Kipnis-Varadon inequality doesn't hold in any amount of sufficient generality, even though the idea might be fairly reasonable. So outside the invariant measure, what do we do? So Cole-Hopf, Nicola, and Varadon several decades ago, several decades ago, told us how to implement the following idea precisely. So because the particle system is moving very fast, at mesoscopic or local scales, the particle system is very close to invariant measure in very fast time, because it's sort of evolving faster than the length scale sort of is adapted to. So as far as local statistics are concerned, we might as well be working at the invariant measure. And the point is that this difference is a mesoscopic local statistic. And if we integrate it on a mesoscopic time average, we expect this thing to be local as well, which means we can apply the Kipnis-Varadon inequality to this thing. And now, to finish the argument, we need to estimate this block average. So if we were at this invariant measure that Matteo very smartly asked about, these etas would be independent mean zero spins. So an estimate for this average could be achieved through sort of a second moment estimate, for example. However, we're not at the invariant measure, so we can't use this sort of elementary probabilistic idea. Instead, what we have to do is we have to remember these etas are really gradients of the height function under some scaling. So we can estimate this block average of spins in terms of some gradient of the height function. And now remember that the height function is supposed to be Brownian, sort of at macroscopic scales. So this is really the question of estimating the regularity of a Brownian motion, and unfolding what that means gives us this n to the -1/2 epsilon estimate that we would have gotten from elementary probability, which is sort of the neat feature of this estimate, in my opinion. One interpretation of this is that the invariant measure estimate can also just be achieved through stochastic analytic estimate, which is, for example, favorable because the stochastic analytic estimate doesn't really care with the initial conditions. It's sort of a consequence of the equation. So in a nutshell, that's the proof. I did have a few more slides going into more detail about the first step, but I'm going to wrap up the talk given that it's close to the end in terms of time by saying that the method that I talked about for ASEP with a slow bond doesn't sort of work only for ASEP with a slow bond. It works for a number, modest, but a number of non-integrable exclusion processes, some of which I've listed here. But I mean, there are other things that are supposed to be described by KPZ. So there are other things that should conjecturally fall into this world of things we should be able to prove things about. So that's what this second bullet point means. And thank you for your attention. Again, thank you for the invitation to speak. And a special thank you to my advisor, Professor Dembo.
Thanks, Kevin, for the wonderful talk. Let me stop the recording.